Hi, everybody. Hope your guys' meeting went well, Amanda and George and Joyce. Hi again. We are here. And I finally updated your class calendar, and I know there were group chats about everything that was going on. So I think I updated everything besides tomorrow we are starting the next section. So we are finishing, hopefully, section 9.3 and the examples today, and homework is due tomorrow. However, you know what? I just said start 9.4, and that's actually not what we're doing. Remember, there are tons of tests, convergence and divergence tests of infinite series. There are tons of tests, and there are 6 sections, 9.1 to 9.6, although 9, this is not you guys, 9.1 to 9.6, there we go. However, 9.1, we did it with our 9.1 from last chapter. 9.2, we just finished. 9.3, we're about to finish. And that's halfway. Was something new where we hit halfway?
Quiz?
Yeah. I think then we'll have a quiz. We need an endeavor quiz, and that's going to happen, but I don't think that's going to happen right away. I want you guys to be able to practice with these tests before necessarily requiring you to state them. So probably I'll save an endeavor quiz until right before the chapter 9 test, which is our chapter 10 intro. You guys know all that. But we are going to have a problem quiz with a random assortment of series and the, how many tests do we have now? Section 9.2 is geometric and divergence. 9.3 is integral and p-series. Those are 4 out of the 9 tests. So we're about halfway through. So we're going to have a section 9.1 to 9.3 quiz just to give you guys the experience of, hey, here are random series. Tell me if they're convergent or divergent and why. And I'm not going to give you any trick ones that you're not able to do yet. That would just be mean. But there is going to be a 9.1 to 9.3 quiz. I'm thinking because of our calendar, the way it is, tomorrow let's go ahead and have go over homework questions day on 9.3 / a review day. I'll have like a little review in the sense of some practice problems randomly assorted, and we have to figure out convergence, divergence. And then on Monday, let's have a 9.1 to 9.3 quiz. So therefore, Georgie, I think you're going to be gone for Disneyland unless Richmond is still sick. If he's sick, then we're good. I mean, that sounds really bad. But if he's not feeling up to it, then we won't have to worry about it. And if you are gone tomorrow, then we're just reviewing. So just check it out over the weekend. All right, cool kids. Is that good?
I saw Richmond today.
Yeah, he's just not feeling good when he came back from Vietnam. So he's trying to figure out whether or not they all feel up to it. I think one of the people can't go and stuff like that. All right, here we go. Boop. Notes. So you want to get these down really, really well, and you guys want to work on homework tonight really, really well. That way you are more prepared and you are continually reviewing for that quiz that's coming. It's kind of a humdinger. It's kind of a humdinger.
What is humdinger?
Humdinger means it's not something to take lightly. If that makes sense. So yesterday we got an interval test done, but we didn't get another interval test done. So let's go ahead and zoom in on this guy. We're going to basically do 1, maybe 2, 3 more examples, and then the P-series test, which is actually pretty quick, and then we're done. Cool? So here we go. Oops, this guy. Question. Before we even think integral test, what should we think? We have 2 other tests. Which ones would you guys test for first?
Limit.
Sure.
Term test.
Let's do the nth term. Just so that we're showing our thinking through process. Not that you have to show this on the quiz, but just to make sure we're thinking through correctly. Take the limit as n goes to infinity of 1 over n squared plus 1. What do we got?
0.
So what do we know?
Nothing.
Nothing.
About this, however, not.
Yeah. That's implied. So nth term is a fail. How about geometric? How do we test? So if we can use him, he's way faster than integrating. What am I going to start doing?
Do the first couple of the...
Yep, so I have 1 plus, what comes next? Next term. Yeah, 1/5. Then what?
1/10.
Then what?
1,
17, right?
Yeah. So,
definitely not geometric, right? times 1/5 times 1/2 times 1 nothing. Anyway. We know it's not geometric, so let's go ahead and go cross that out and say no. But we are going to go to our integral test, right? So we're going to head to integral. But before we can start the integral test, this is what I failed to do yesterday. Before we can start the integral test, question, what do we have to do first?
Recheck things.
3 checkpoints. So, looking at our function, question, is 1 over n squared plus 1 continuous?
Yes.
Yes, because the discontinuity would be an imaginary number, true? Okay. Is it positive? It meaning its sequence of terms?
Yes.
Yes. Is it decreasing?
Yes.
This is where you guys got a little stuck mentally yesterday, but now that you're looking at it, it's a yes, right?
Yeah. When you mean positive, you mean like 1 plus 1/5, 1 plus 1 10 plus 1.
Are all positive.
Gotcha.
The only way it could be negative is if it starts with like, what could be an example? Not this one. If it starts with maybe a negative number, but then it turns positive and will never go back, then we could split up the series to start at the positive terms and have the negative ones be separate. That's our one way of getting around it. But if it's alternating, if it has all negatives or every other negative, it's a no integral test. So therefore, can we do the integral test? Yeah. So how?
Integrate.
Well, consider, right? Consider the integral from 1 to infinity of 1 over x squared plus 1 dx. Is that good?
Can we leave it just 1 over n plus 1, n squared plus 1 dn?
Technically, the notation would be incorrect since n is used for sequences in series, and x is used for integrals. But I see what you're saying. But I'd rather not.
I'll be George for a second. Oh, schmutz.
George, you should feel honored. All right, so we need to solve that integral, right, guys?
Yeah.
Okay, we're following the same procedure, so let's keep going. Can I actually make myself a little more room? Hold on, there we go. How do we integrate? This one's easy. Arctan, you got it. Improper integrals, so you have to consider that as well. We have our limit as b goes to infinity of arctan of b minus, right? This is just arctan and back, so we're just plugging and chugging. Making myself a little more room so I can get it. Minus arctan of 1. Who is arctan of 1?
4, right?
Mm-hmm. And what's going on with arctan of b as b goes to infinity?
Pi over 2.
Does that make sense? Are we all tracking on pi over 2? Arctan reflected, limited by the vertical asymptote, which is now horizontal asymptote. So yes, we can go ahead and say this guy is just approaching positive pi over 2 because we're approaching positive infinity. With sequences in series, you're not going to approach negative infinity. But an improper integral, if you were approaching negative infinity, what would be the answer for arctan?
Negative pi over 2.
Exactly. So then our final answer is pi over 4, right? What does that tell us? What does that tell us?
The series converges.
Yes. Yes. If the limit of, or I should say, if the improper integral is a constant, doesn't that technically mean, according to the integral test, that the integral converges? Does it say what the integral has to converge to? No. If the integral converges, then the series converges. So you have to make sure you don't confuse this with the nth term test, which is for us testing the sequence of terms of the series. In that, if the limit exists for an improper integral, then we can say the integral converges, and hence we can say the series converges. So by the integral test, I don't know what that was, sorry. By the integral test. Since the integral of or from 1 to infinity of 1 over x squared plus 1 dx converges, then this series 6. Don't need the then, do we? That's the whole dramatic thing. We're done. The series converges as well. Now, hold on. Am I saying what the series converges to?
No.
No. I'm saying just that it does converge. We do not have any information without going to our calculator and plugging into that little thing that we did before for exploration's sake and seeing what happens as we include more terms and more terms and more terms and more terms and more terms. See if we can find some sort of convergent value, or values converging to. But that is not our job. Our job is in this problem. And the only thing the integral test does is say converge or diverge, okay? Okay. How about this guy? We're going to go kind of quick. I'm not even going to do it too much. Nth term test, yes or no? No. Geometric series test. Well, hold on. We got to figure out decreasing anyway if we have to go integral, right? So we have 1 over 2 ln of 2 plus 1 over 3 ln of 3 plus 1 over 4 ln of 4 plus, definitely not geometric, right? Forget that. So we know we are doing our integral test, but for our integral test we have to test for a few things. First of all, continuous.
Mm-hmm.
No, not at 0, but wait, what are our bounds? It is continuous on the integral, right? How about positive? Yes, but be careful, is ln always positive? As long as it starts at 2, we're okay. If it started at 0, would we be in trouble? Yeah, we'd be in trouble 2 ways, for the continuous and for the positive. Okay, let's keep going. Positive is a check. How about decreasing?
Nope.
Uh-oh. Why?
It's always going up. Very slowly at that, but it's always going up.
Careful. Who's going up? Numerator or denominator?
Okay.
Struggle. But Gerardo's right. ln is always going up. It's ln of 4, ln of 27, ln of 64. No. 256. Anyway. The denominator is going up, but that means the entire number is going down, right? So therefore, decreasing is a check. Now, I'm going to go ahead and consider the integral.
I was so dumb. That was the first thing I noticed, and then the first thing I noticed, oh, it is decreasing. Then right after that, I said it isn't.
It's okay. Well, you were focused on the denominator, though. That makes sense. That happens. All right, kiddos, how do we solve this integral? Can I do this?
Oh, wow. Oh, just you so.
Yeah, who's you?
Me.
No.
ln of x.
Does that make sense, guys? Mm-hmm. And du is equal to 1 over x dx. This is just a simple use of in that. We can go ahead and just say this would be the integral of 1 over u du, right? How do we integrate 1 over u du? Well, that's weird.
ln of ln.
Yep. Turn the limit as b goes to infinity of ln of x.
Absolute value.
Ooh. Absolute value where though?
ln absolute value. ln.
Yeah, just this one.
Or ln of b, I should say.
From? Yeah. I don't like my brackets getting in my way and making my notation here.
Misty, when we express the limit, do we say the limit equals? Or is it not right?
No, we said limit equals for the improper integral.
No, but just regular limits.
So then we have ln of b. Oh no, wait, it's a limit. My bad. I'm showing bad habits. We should sue. limit as b goes to infinity of ln of ln of b minus ln of 2.
Well, it diverges.
Okay. ln of 2 is a constant, of course. ln of b. Well, just think about it, cool kids. ln of b is approaching what?
Infinity.
Infinity. And what's ln of infinity going to approach?
Infinity.
Infinity minus a constant? Still infinity. Therefore, since my limit is infinite, what's my conclusion going to state? Sorry.
Integral diverges, and because of the integral test, so does the series.
Got it. Oh, I'm writing last example. There's one over x, ln of x, right? Done. You guys already start looking at the next example? Ooh, that's a fun one.
And we know nothing if we use the nth term test.
We know nothing because, yeah, tangent inverse is definitely weaker than n squared. Tangent inverse has a horizontal asymptote, it's capped anyway. So therefore, nth term test is a no. Geometric series? Yeah, no. Tangent inverse of 1, what would that be? Pi over 4. All over 2. Tangent inverse of 2. Something yucky.
You know, earlier I rewrote arctan, and I wrote arctan, but I put a negative 1 at the tan, tangent to arctan inverse.
Oh. You're just being redundant. That's okay. Having too much fun. Okay, hold on. With this, kiddos, of course we're going to integral test because geometric and nth term, yeah, not cutting it. We know that continuous, we're okay because arctan is always continuous, right? For all real numbers. N squared plus 1 can't be a 0, so that's okay. Positive? Yes, because arctan from 0 to infinity is positive, so that's okay. Decreasing.
Of course,
Why?
because the bottom is strongest.
That's not necessarily enough to say decreasing, though.
Well, it makes the whole thing converge to 0 if you take the limit. So
True, but still doesn't mean that it's strictly decreasing. It could go up and then down. I'm just saying this because I've seen ones that do it to so that's fine. How do we know for sure, if we don't know tangent inverse of 2, that this strictly is decreasing?
Derivative!
We could start plugging in and getting decimals. We could do a derivative and a sign chart, or we could just think about what we know about tangent inverse.
Always
Tangent inverse is strictly
increase.
increasing. We don't have to worry about the negative part because we're just looking here anyway, right? From 1 to infinity. But tangent inverse is always increasing, right? But by how much? What's it approaching again? Pi over 2. What is pi over 2 as a number?
Like,
1 point
yeah, 1 point
something. 1.5-ish? A little bit more, 1.6-ish maybe? So if this is 1.6-ish, and that's the highest it can go, if I go from pi over 4 to something a little bit bigger, question, do I have to worry if my denominator is increased by 3? You see what I mean? Who's increasing faster? Yes, the denominator. However, my question is there any way it's going to go up and then down? And the logical answer, since we're not having to prove it, is no. It's going to keep decreasing. The numerator from the very beginning is increasing slower. Does that make sense, guys?
Um,
I'm
So-
just showing that because some functions do go up and then go down. We're going to have to watch out for those things.
So we just know that it's not going to go up and down. We just know for a fact it's not.
We know that between tangent inverse of 1 and tangent inverse of 2, there's no way it increased more than 3. The denominator increased by more than the numerator. Does that make sense? Yeah. So therefore we can say, yes, the function is strictly decreasing from the very beginning without having to find all the nasty derivative stuff. Okay. Now what?
Oh, what?
Nope, we say consider. Party pooper. Consider the integral from 1 to infinity of tangent inverse of x. This one's not too bad if you look at it. All over x squared plus 1 dx. Has anybody gotten to figure out how we're solving this puppy? You, son. Who's my you? Arctan. Good. U is equal to tangent inverse of x. Du is equal to 1 over x squared plus 1 dx. So this is going to end up being u du, right? Why am I running out of room? So therefore we have the limit u squared over 2, so we could have 1/2. U squared would be tangent inverse of b squared minus 1/2 tangent inverse of, what was my lower bound? 1? Oops, I didn't. Squared. It's going to equal. Tangent inverse of 1, can't we just say that's pi over 4? And pi over 4 squared, can we just make that pi squared over 16? Times 1/2, pi squared over 32. But long story short, we have to figure out what's going on over here, guys. What's tangent inverse approaching as we go towards infinity? Pi over 2. Pi over 2 squared is going to be pi squared over 4. So then I'm going to end up with 1/2 pi squared over 4, pi squared over 8 minus pi squared over 32, which would be 4 pi squared minus 1 pi squared. Is it 3 pi squared? Good. Wait, over 16 or 32? I think it's 32. So it's 1 pi squared over 32, and then 4 pi squared over 32, right?
I'm agreeing.
So then 3 pi squared over 32. Anybody else? You guys all good? Okay. Oh wait, but we shouldn't box that. That's not our answer, but it does tell us our answer. What's our answer going to be?
By the integral test, since the infinite integral, or the improper integral converges, the series converges.
Wait, what?
By the integral test, since the improper integral converges, the series converges.
Oh, okay. I thought you said diverges.
I hope I didn't.
Making it fit. Ha! Okay. Integral test. How are we doing?
Not that bad.
It's not that bad, unless the integral is hard. But good thing we've been practicing integrals for quite a while, huh? We're just going to put it to good use. Now, we have one more test. And he's actually another easy one, praise the Lord. The integral test is a little bit harder. P series. We like him. And this is because of, in section 9.4, the day I was gone, you guys watched the video from an old class, we talked about, was it the integral of 1 over n to the p?
Something like that, yeah.
Or
Oh,
was it
it was
sequence? It was the sequence.
No, it was the improper. From
Oh, improper.
1 infinity of 1 over n.
Got it.
X.
So we talked about 1 over x to the p. That's one that we could have made an Endeavor card, and I almost did, but I ended up, when I updated the Endeavors online, I didn't make it an Endeavor card because we have the p-series test, and this is when we really have to use that property. P-series test says when we have not the sequence, but the series from 1 to infinity of 1 over n to the p. I don't remember what was there before, but whatever it was, I didn't like.
It was just sigma 1 over a to the p.
Oh, ew, yeah, I don't like that.
Why a?
I don't like a because a makes me think of like the nth term. So I'd rather have n because that's how our notation has been for all of our sequences. Or sorry, all of our series. So the summation from 1 to infinity of 1 over n to the p. Who to the p? N to the p. Who's n? The variable. Anybody else? No. So not n plus 1 to the p, not 2n minus 3 to the p, not 5 to the p minus 2, no. Or sorry, n to the p minus 2, that's a no. So whenever I have 1 over a variable to the p power, I can say the series will converge when? Do you guys see it?
If p is greater than 0 and diverges is 0.
There's another reason why we like the p-series test. He doesn't just prove convergence, he proves convergence and or, no. Convergence or divergence. Or divergence based upon p. So he's one test that can do 2 things. We like those. This is Endeavor number? Yeah, try it.
Something can diverge and or converge, like Gabriel's horn. Converges.
Yeah, but 2 different quantities. So each quantity either converges or diverges.
Dang it.
So an object that we're measuring, you know what I mean? That's what it is. Sorry, what Endeavor was it? I lost track.
I think 14.
14. Wait a minute, what if p equals 0? Why isn't that up here? Because remember, this is only p greater than 1 and p between 0 and 1. No negatives and no 0. Let's write it. What if it was 0? We would have n equals 1 to infinity of 1 over n to the 0. Wait, what's everything to the 0 power? What's 1 plus 1 plus 1 plus 1 plus 1?
Infinity.
Yeah, but that wouldn't be the p-series test. That would be the divergence test, right? We could just say the limit as n goes to infinity. Does that make sense? We wouldn't be using p-series. We'd be saying, hey, the limit as n goes to infinity of 1 is 1, so that's not 0. Okay, it diverges. Is that cool? Okay. What if p is less than 0? Yeah, you see that? Because then we would have n equals 1 to infinity of 1 over n to the, let's just say negative a for right now. So we'll say, we'll set p less than 0 equal to negative a, just for sake of seeing what's going on. So that would go ahead and flip to be n equals 1 to infinity of n to the a. Hold on. That's not really a p-series either, because it's not 1 over. It's truly on top instead of on bottom. And probably we would use a different test as well. Probably. Depends on what a is, I suppose. But probably diverges by nth term again. Because if that's any positive number, and if n is all the integers, well then that's going to be just approaching infinity. The limit's going to not exist, therefore by the nth term test, my series is going to diverge.
Hey, Steve.
Yeah.
On a piece of paper, you want us to put it all in our spirals later, or just say?
Well, I want actual sections in your spirals, and I want the Endeavor cards. I'm not forcing you to put the examples in your composition books unless you want to. Does that make sense?
It was 9.2 and this one's like 9.3.
So therefore, we're not going to do all of these, let's just do like the first three. I could rewrite this one. Can't I pull the 2 out, kiddos?
Absolutely.
I have 1 over n to the 1. What does P series tell me?
Diverges. What's it called? P series?
P for power. What about number 2? Mm-hmm. Once again, we do not know what it converges to, we just happen to know, not just happen, according to the test, we do know the series converges. How about number 3? Hopefully you're not writing by P series test, because it's not. Right? By the nth term test, what are we going to say? Since the limit as n goes to infinity of 3n is infinity, not 0. So keep your eyes open, kiddos. But that is the P series test. Alright, might be good to the rest of the examples tomorrow, possibly. But for today, let me go ahead and let you guys see the homework. If you have your spirals, you can write it down real quick. You want to do that? Let's get them up.
Are we supposed to finish the examples for homework?
No, you're doing book work.
See, I'm about to get into the section 3 where the analysis is supposed to go in my spiral. Is it okay if I do homework there, or should I?
That's okay. So we're doing, we probably won't do a lot of warm-ups, if any, for the rest of the year, because we're getting ready for the AP approval. Hey, look, I have a problem from 9-1 and a problem from 9-2. Oh, you guys don't have 9-1. Okay, ignore all the 9-1 problems. Lame sauce. You can't do those.